Hello, this talk is about the VoiceMOS Challenge 2023, Zero-Shot Subjective Speech Quality Prediction for Multiple Domains. For some background, our topic is speech quality assessment for synthetic speech. If we're building speech synthesizers, such as text-to-speech synthesis or voice conversion, it's important to evaluate our models, and we typically do this using a subjective listening test with human listeners. One very popular type of test is the mean opinion score test, or MOS. In a MOS test, listeners receive synthesized samples one by one, and they rate them on a scale, typically from 1 to 5, to answer some question, such as how natural does it sound. As you can imagine, this type of test is very expensive and time-consuming, so this motivates us to consider data-driven MOS prediction, in particular, data-driven MOS prediction based on deep learning. A downside that we've observed with this type of MOS prediction is that there's typically bad generalization ability to new contexts and domains, such as new types of synthesized speech. To address this challenging topic of mean opinion score prediction and generalizing to new domains, we started running the VoiceMOS Challenge series starting in 2022. This challenge is for encouraging research on this topic to compare different approaches using shared datasets and evaluation, to focus on the challenging question of generalization ability, and to promote discussion about the future of this research field. So the first iteration of the challenge was last year, and just for some background, in last year's challenge, we had two tracks. We had the main track and an out-of-domain track, or OOD. So for the main track, we used a data set called BVCC. This is a very large-scale data set of synthesized speech samples from 187 different systems, all rated together in one listening test, so we also have their MOS ratings. And for the challenge test set, we held out some unseen systems, unseen listeners, and unseen speakers. We also had an out-of-domain track. This was data from a completely separate listening test, and this was Chinese language synthesis as opposed to English language, as in BVCC. And these were all systems from 2019, in particular for the 2019 Blizzard Challenge. These were team submissions for that, so these are a variety of text-to-speech systems for Chinese. So the test set, we also held out unseen systems and listeners. The purpose of the out-of-domain track was to reflect a real-world setting where only a small amount of labeled data might be available. So for the out-of-domain track, we provided only a very small amount of labeled data for participants for training, as opposed to the main track. So after we ran the challenge last year and analyzed the results, we found that, in fact, in the out-of-domain track, unseen systems were quite a bit more difficult to predict for the teams. And some feedback we received from the teams were that they would like to see MOS prediction for more languages and more speech types, for example, speech and noise or music-related voice, such as singing synthesis. So that brings us to this year's challenge. So following on the results from last year and the team's feedback, we wanted to really focus on this out-of-domain scenario. And this year we actually did zero-shot out-of-domain MOS prediction. So all of our tracks this year, we had 3 tracks this year, and each of them was out-of-domain compared to we didn't have one in-domain track. So, and to address the interest in more types of voice audio, our 3 tracks were French speech synthesis, singing voice conversion, and noisy and enhanced speech. And the reason why it's zero-shot is because no official MOS-labeled training data was provided for the French and singing tracks. For the noisy and enhanced track, we made use of the TM-hint-QI dataset, which has different types of noise and different speech enhancement systems and their MOS ratings. So this is actually a real world and challenging MOS prediction task. And we did this in collaboration with ongoing speech synthesis competitions. So the singing voice conversion data came from the Singing Voice Conversion Challenge, which was running at the same time. And the French speech synthesis, the samples came from teams' submissions to the Blizzard Challenge. So this was a really nice collaboration. We received synthesized samples from these challenges team submissions, and VoiceMOS participants had to make MOS predictions before the actual listening tests for these challenges were completed. So this is actually very real world and challenging MOS prediction. So here's a summary of the data sets. So track 1 was the French speech synthesis, and it actually was broken into 2 subtracks. So for Blizzard this year, they had a main hub track, which was a large amount of data from a single speaker for building a speech synthesizer. And the spoke track was a speaker adaptation task where there was a much smaller amount of adaptation data for a target speaker. So again, why zero shot? Because this matches the real actual use case for MOS prediction. In a real scenario where we're building a completely new synthesizer, maybe for a new language or a new speaking style or a new type of voice audio. So if this is the case, then we won't have any past samples or their MOS ratings to train or fine tune a MOS predictor. So that's why the zero shot condition is so important and why we focused on it this year. And basically we want to try and see whether general purpose MOS prediction is possible in this kind of zero shot scenario. So as for the rules and timeline, so we didn't provide any official MOS labeled training data this year, although we did provide pointers to relevant data sets with MOS labels such as BVCC. And we also provided for the track 3, the noisy and enhanced speech, we had training data for that. That was the TM Hint QI data set. So we had 3 phases. In the leaderboard phase, teams could submit predictions for the track 3 noisy and enhanced speech development set as many times as they wanted. And we had a public leaderboard on the CodaLab challenge platform so that the participants could compete with each other and see how they were doing on the leaderboard. During the evaluation phase, we released the test set audio samples to participants, and participants must make their predictions. Teams could make up to 3 submissions with their predictions, and we did not have a leaderboard for this phase since ground truth MOS was not available yet. And finally, in the post-evaluation phase, we really wanted all the teams to try to do all of the tracks. But of course, this didn't happen. So after the evaluation phase, we ran a short post-evaluation phase where we encouraged teams to just try running their systems on the tracks that they hadn't tried already. So our evaluation metrics were the same as last year. So we have both system and utterance level evaluation metrics. Mean squared error is simply the difference between predicted MOS and actual MOS. And then we have 3 kinds of correlation. And our main correlation metric was, like last year, system level Spearman rank correlation, because this measures ranking order, which is system level ranking order, which we decide is what we care about the most for the purpose of this challenge. As for baselines, we had 2 baselines. The first one was the SSL MOS baseline. This is a very simple fine-tuning of a self-supervised wave-to-vec2 model that we fine-tune using the BVCC dataset. And the second baseline was UTMOS, which was the top team from last year's challenge, and they open sourced their code and shared pre-trained models. So we use that as a baseline as well. Now for the results. We had 10 teams from academia and industry participating from 7 different countries. The noisy and enhanced track was the most popular one, probably because we provided some training data for that. And we found that it was difficult to predict all domains well with a single system. So We have in blue the 2 French speech synthesis tracks. Red is singing voice conversion, and yellow is the noisy and enhanced speech. And these hashed bars are results that came in during the post-evaluation phase. So you can see that there's very varied results for each track. And in fact, the team that had sort of the most consistent results for all of the tracks told us in their system description that they actually had slightly different model architectures and used different training data for each of the tracks. Interestingly, we thought that the singing voice conversion task would be very difficult, but teams did pretty well on this track. And in fact, we learned that none of the teams used singing data in developing their models. So this was surprising. Another surprise was the difference between the 2 tracks in the French synthesis. Most teams did very well on one and less well on the other, and this wasn't consistent in any direction. So this was surprising as well. So we can look more closely at for example, the noisy and enhanced predictions. So we have actual MOS versus predicted MOS for all of the teams. We have several different types of noise and several different types of denoisers and speech enhancers, and several different signal to noise ratios in the data set. And we can see many of the teams have these kind of outliers that tend to be these blue squares and triangles. So actually these 2 systems represented by a triangle and square were also the unseen systems as well. So these were more difficult to predict. So finally, we can look at some conclusions. The goal of having one model that can predict MOS well for various different domains, I think we can say we haven't reached that goal yet. It's still an open problem. The domain mismatch between singing voice conversion and text-to-speech synthesis was not as large as we expected. The difference in predictability between speaker-dependent and speaker-adaptive French TTS was surprising. And from the system descriptions that we received from the teams, we noticed that approaches using listener information and a mix of training data sets tended to be the more successful approaches. Finally, we can still observe a gap between the case where a small amount of in-domain training data is available versus the completely zero-shot setting. This is represented by track 3, noisy and enhanced speech, where we provided some training data. So that's all, and we hope you will consider joining the VoiceMOS challenge next time. Thanks very much.